Hello dear students, before we start doing anything, let's look at this circuit. As you can see, this circuit consists of a plug K, a resistor R, a battery and a thick copper wire XY. We all know copper is a good conductor of electricity. Now I am putting a compass needle nearby to this copper wire and passing the electric current by inserting the key into the plug. You can see that as current flows in the circuit, the compass needle has started deflecting. Now observe the change. In the deflection, as I am changing the polarity of the battery, the needle has deflected in different direction. You may be wondering why this has happened. This is because when electric current passing through a copper wire, it gives rise to a magnetic field. It means the magnetic field and the electric current are linked with each other. This is the other effect of electricity rather than heating effects.
Hans Christian Ørsted, a Danish scientist from University of Copenhagen, Denmark, was the first person who found that electricity and magnetism were related phenomena. While preparing for an evening lecture on 21st April 1820, Ørsted developed an experiment which provided evidence that surprised him. As he was setting up his materials, he noticed a compass needle deflected from magnetic north when the electric current from the battery he was using was switched on and off. This deflection convinced him that magnetic fields radiate from all sides of a wire carrying an electric current just as light and heat do, and that it confirmed a direct relationship between electricity and magnetism. His research later created technologies such as radio, television, and fiber optics. The CGS unit of magnetic induction, Ørsted, is named in honor of his contributions to the field of electromagnetism. In this chapter, we will study the magnetic fields and its electromagnetic effects. We shall also study about electromagnets, electric motors which involves the magnetic effect of electric current, and electric generators which involves the electric effect of moving magnets. The word magnetism originated from the place Magnesia, where natural magnets were first found. Magnetite, Fe3O4, which is an iron ore, behaves as a natural magnet. In earlier time, magnetite was known as lodestone. A magnet can be demagnetized by heating, hammering, and keeping in fast alternating current. Magnets are used in speakers, on the hard disk and floppies for computers, on audio and video cassette tapes, in children's toys, in almirah and refrigerator doors to keep them shut, and also in medicine.
Today we will talk about the magnetic field and magnetic field lines. Direction of magnetic field produced due to a current carrying conductor. Before I explain magnetic field and magnetic field lines, let us see what is a compass needle. A compass needle is a tiny bar magnet. which is free to move in the horizontal plane. The ends of the compass needle point approximately towards north and south direction due to the magnetic field of Earth. Now some question must be arising in your mind. What is a magnet? I will show you. A magnet is a thing which attracts nickel, iron, cobalt. See. It attracts the iron, a magnet has two poles, north pole and south pole. The north pole of the magnet points towards, when freely suspended, to the north direction of the pole, and the south pole, which is towards south of the earth, shows the south pole. Now I will show you some activities of the magnet. As you can see, this is a magnet. It is the north and here is the south. If I will take two like poles together, it has been found by experiments that two similar poles repel each other and two unlike poles attracts each other. So the north pole and the south pole attracts each other, and south pole repel each other. Similarly, north pole and north pole repel each other. Now, what is a bar magnet? A bar magnet is a long magnet of rectangular shape and the uniform cross-section area. Then this question may be arising in your mind: why does a compass needle get deflected when brought near a bar magnet? See, I am bringing a compass needle near the bar magnet. Now see what is happening. A compass needle, when brought near a magnet, it deflects. Near the pole, it deflects maximum because the bar magnet exerts a magnetic force on the compass needle. See. Now we will learn about the magnetic field and magnetic field lines. The space surrounding a magnet in which magnetic force is exerted is known as magnetic field.
Take a board. Place a bar magnet in the center of it. Sprinkle some iron fillings around the bar magnet. Now, tap the board gently and observe the iron fillings. Iron fillings arrange themselves in a pattern as shown here. What does this pattern demonstrate? It indicates that near the magnet, iron fillings experiences a force, and this force makes iron fillings to arrange in a pattern. The region surrounding a magnet in which the force of the magnet can be detected is known as magnetic field. These magnetic fields are stronger near the poles and in other areas are less or weaker.
The magnetic field has both magnitude as well as direction. The north end of the needle of a compass indicates the direction of magnetic fields at that point where it is placed. A magnetic field is described by drawing the magnetic field lines. The magnetic field lines are the lines drawn in a magnetic field along which a north magnetic pole would move. Therefore, it is taken by convention that the field lines emerges from north pole and merge at the south pole. Inside the magnet, then what is the nature of the magnetic field? Inside the magnet, the direction of field lines is from its south pole to its north pole. Thus, the magnetic field lines are closed curves, as you can see. Now, you can draw the field lines along a bar magnet. Let us do an experimentation. Fix a white drawing sheet on a drawing board. Place a bar magnet like this and draw its boundary. Now bring the compass needle to the north pole of the magnet. See what happens. Needle got deflected. Now put the point where is the ends of the needle is. Now take the compass needle and put the compass like this, and again put a dot. Repeat the experiment like this. Now see what you will observe. Goes on doing this, then you will see these magnets are giving you a pattern. We have started from the north pole and ending towards the south pole. Now join all the points. We have started from the north, so put arrows like this. This is magnetic lines of force. As many as lines you want, you can draw it. Now after drawing the magnetic field lines, you can say the magnetic field lines originate from the north pole of a magnet and end at its south pole. The magnetic field lines come closer to one another near the poles of a magnet, but they are widely separated at other places. The field is stronger, that is the force acting on the pole of another magnet placed in there where the field lines are crowded. The magnetic field lines do not intersect each other. Now I think you will be able to answer these questions. Which is the sure test of magnetism? Repulsion is the sure test of magnetism and not the attraction. Does a stationary charge produce a magnetic field? No, only a moving charge produces a magnetic field. If a bar magnet is converted into two pieces by breaking it, how these two pieces behave? Both the pieces will behave as magnets, each having north pole and south pole. Okay, So before we end this episode, now let us look at what we have learned today. We have proved a major point in today's lesson was that the electric current produces magnetic field. Second, electricity and magnetism are linked with each other. Third, what is a magnet? Fourth, how magnetic compass works. Fifth, when current flows from a wire, a magnetic field generates. Sixth, we also learn to chart magnetic field lines. Seventh, magnetic field changes when a change in the direction of current flow. Before we go ahead, I expect all of you revise whatever we have learnt today. So it's going to be easy for you to understand next portion. Till then, goodbye.